Join me today as we tour the Hertzsprung-Russell diagram to learn all about the secret lives of stars. Imagine taking a picture of all the people in a small town, like my town, Valdez, Alaska. What if you could sort everyone in this photo of young to very old? Well, in that one image, you could take a snapshot represent in all stages of the human condition. And this is exactly what astronomers do. The Hertzsprung-Russell diagram is one of the most important tools for learning about stars. Now, instead of just a town photo shoot, imagine the Hubble telescope is zooming in to photograph a star cluster. The beauty of star clusters, for one like the Pleiades, is that all of the stars within this group that are concentrated were formed at the same time and are relatively the same distance from an observer on Earth. This means when the astronomers measure the luminosity of all of the stars in the cluster, that there is a true relative value, that the brighter stars that appear more luminous really are brighter compared to the dim red stars in that cluster. There's a video, and I love watching this video. It has all of the stars taken from such a star cluster, and then it organizes the stars. This video sorts all of the stars by color first. Then it sorts them by their relative luminosity or brightness. What is the result? A real-life Hertzsprung-Russell diagram. There's a beauty and a visual representation to the stars. We'll start with luminosity on the left side, labeled luminosity L for the sun, and the sun is 1. The scale is logarithmic. If it was not logarithmic, the y-axis could not fit on the paper. One step on the axis is 10 times brighter than the previous, and 2 steps is 100, 3 steps 1,000. Along the bottom of the diagram, you can see the spectral classes. O is on the left, and on the very far right is class M. Spectral classes of stars are determined by looking at a starlight through a prism, and then a unique fingerprint is revealed of the starlight. All of the stars that have similar spectrum are grouped together. The ionization state indicated by the spectrum represents the star's effective surface temperature. When these stars are put in order from the hottest on the left to the coolest stars farther to the right, we end up with the OBAFKGM that you see on the bottom of a diagram and that you can remember as "Oh, be a fine girl or guy, kiss me." The hottest stars on the left are blue. The white and yellow stars you'll see in the middle, and the coolest red stars are on the right of the HR diagram. This range of temperature on the x-axis ranges from 30,000 Kelvin to 3,000 Kelvin. So you'll see stars up on the upper left. Rigel and Spica, these upper left stars are hot and luminous, while the stars on the upper right are cool and luminous, like Betelgeuse and Antares. If we go down on the lower left, those stars are hot and dim, known as white dwarfs. And the lower right has the cool and dim stars, like Proxima Centauri, the nearest star that we know of. This diagram has information about the relative size of stars as well. You'll see that the larger stars are on the top, going down, and the bottom stars smaller in diameter. Some Hertzsprung-Russell diagrams actually have circles to indicate this. Circles are not to scale. The giants and the hypergiants would be so big they, again, would not fit on the paper. Okay, on the big picture, let's look at the 4 groups of general types of stars that are on the Hertzsprung-Russell diagram. You'll see this diagonal line going from the top left down to the bottom right. That is fondly known as the main sequence. 90% of the stars in the universe fall on the main sequence. Notice that our sun, a G-class star, is right in the middle of the main sequence. We have an average star in terms of size and temperature and luminosity, and so it's easy to use it as a standard comparison for the rest of the stars. All the stars in the main sequence have one thing in common, and that's their diet. They are all consumers of hydrogen. Main sequence stars undergo nuclear fusion, fusing their hydrogen into helium. The more massive stars, the more hydrogen there is, the bigger they are, the hotter, the more luminous, and the faster they burn out. Those are the top left, the blue stars. The stars on the main sequence that are smaller are red dwarfs down on the bottom right. They have a smaller mass and are very efficient at fusing their hydrogen into helium. They can live a long, long time. And whereas blue stars can live for millions of years, and a star like our own sun will live in the billions, red dwarfs will live in the trillions of years. Okay, that was the main sequence. The next group we're going to look at are the giants, and those are located to the right of the main sequence. Giants are no longer able to fuse hydrogen into helium, so they expand and cool down and shine by fusing their accumulated helium in their cores into heavier elements. It's just their huge size that makes them bright. Think of a 25-watt light bulb, an incandescent light bulb, and it's not going to put out a lot of heat or a lot of luminosity. But if you put a couple thousand of them together, it would be much brighter and more luminous. The next group on the chart are the supergiants. They're located above the giants. And the reason why they're supergiants just has to be what they're given or endowed at birth. The supergiants started out as more massive stars and evolved into supergiants. And as they grew and expanded and became even larger, they were even more luminous. So they moved up in their luminosity as they aged. Okay, we're on to the final group, the lower left. These are known as the white dwarfs. They're the final evolutionary stage of low to intermediate mass stars. They're very hot and bluish, but have low luminosities because they're very small. You're going to learn that there's two basic groups of stars. They're ones that are above a certain mass that turn into supergiants and have a different lifestyle and end up in a different way. And you'll learn about the low mass stars. We've got the high mass stars and the low mass stars to look forward to as we learn more about the lives of stars. For now, study the Hertzsprung-Russell and become familiar with it because it's going to help you for the rest of the class.